In the name of Allah, in this lecture, we will talk about the most important types of conductors used in overhead transmission lines. To begin with, we must understand that the main component of an overhead transmission line is the conductor, while the other parts or components of the line are auxiliary components whose function is to support the conductor and insulate it from the ground. This is because the conductors or wires are responsible for transmitting electrical energy or electrical power from one station to another. The second important point is that the conductors used in overhead transmission lines are not insulated, meaning they are bare conductors, not covered with any insulating material. These conductors or wires are suspended between the towers of the overhead line, and as I mentioned before, the distance between one tower and the next is called the span. I also mentioned that the conductor or wire is suspended between the towers of the overhead transmission line, and as long as the conductor is suspended, it is naturally subjected to the effect of its own weight. This causes a tensile stress in the downward direction. Therefore, one of the most important technical specifications of conductors or wires used in overhead transmission lines is that the material from which the conductor is made must have high mechanical strength in order to withstand the tensile stresses acting on it due to its own weight, as we have explained. The second important requirement is that the material used to manufacture the conductor should be lightweight in order to reduce the tensile force acting downward on the conductor as much as possible. It is well known that there are many types of conductors used in overhead transmission lines, and each type is made from a different material. Therefore, we need to understand, in general, the factors or criteria on which the selection of the conductor material or type used in overhead transmission lines depends. Factor number 1, the distance between the two towers. Factor number 2, the tensile force acting on the conductors, which is of course due to the weight of the conductor or wire. Factor number 3, whether the transmission line is subjected to vibrations caused by wind or whether it is relatively stable and steady. In other words, whether the line is located in an area with strong and continuous winds or in an area where the weather conditions are relatively stable. Factor number 4, the power loss along the transmission line route. Of course, everyone knows that the resistance of a conductor is equal to the resistivity multiplied by the length of the conductor divided by its cross-sectional area. Also, the power loss is equal to the square of the current multiplied by the resistance. Therefore, the type of conductor material determines the resistance of the conductor. Naturally, the longer the line or the conductor, the greater its resistance, and consequently, the greater the power loss. Factor number 5, the voltage drop. We also know that the voltage drop is equal to the product of the current and the resistance of the conductor. This means that as the length of the transmission line increases, the resistance of the conductor increases, and therefore the voltage drop also increases. Hence, we can understand that the material from which the conductor is made directly affects the resistance of the conductor, and it has a significant impact on both the power loss and the voltage drop calculations. Factor number 6, the weather conditions or climatic environment along the route of the overhead transmission line. Factor number 7, the cross-sectional area of the conductor, or the number of conductors per phase, that is, the bundled conductor system. In other words, whether each phase consists of a single conductor, two conductors, or more than that. Now we have understood the most important factors or considerations on the basis of which the conductor material used in overhead transmission lines is selected. But the very important point that we must know is, what are the most important characteristics or technical specifications of the conductor material used in overhead transmission lines? First, the conductivity. Of course, the material from which the conductors or wires of overhead lines are manufactured must have high electrical conductivity. High conductivity means low conductor resistance, which in turn results in lower electrical power loss and less voltage drop. This ultimately leads to economic savings and energy conservation. Second, the mechanical strength. We must understand that the mechanical strength of the conductor material is measured by the maximum stress that the material can withstand. As mentioned earlier, the conductor has weight, which creates tensile stress, pulling the conductor downward. Therefore, the greater the ratio of mechanical strength to weight, the larger the distance that can be maintained between transmission towers. This reduces the number of towers, which in turn means lower construction cost for the overhead transmission line as much as possible. Third, the modulus of elasticity. The modulus of elasticity of the conductor should be low so that the conductor does not elongate excessively under the tensile stress caused by its own weight. Excessive elongation of the conductor leads to a weakening of the conductor and may eventually cause it to break. Fourth, and one of the most critical properties of the conductor material, is the coefficient of thermal expansion. The conductors or wires of overhead transmission lines must be made of a material with a low coefficient of thermal expansion because these conductors are bare, not covered with any insulating material. Therefore, any increase or decrease in temperature will directly affect the conductor itself. If the conductor has a high coefficient of thermal expansion, this means that during summer or high temperature conditions, the conductors will experience significant thermal expansion. Such expansion may cause the conductors to sag excessively, bringing them closer to the ground or even into contact with each other, which would be a serious hazard. Secondly, if the coefficient of thermal expansion is high, then during winter, the conductor will undergo significant contraction. This contraction leads to an increase in tensile stress within the conductors or wires, which may eventually result in breaking of the conductors. Fifth, the cost. Of course, it is very important that the economic cost of the conductors, or in general, the construction cost of the overhead transmission line, be as low as possible, while still maintaining the technical and engineering requirements of the line. That is why we find that the most commonly used conductors in overhead transmission lines are made of aluminium, because it is light in weight, and secondly, because it is much cheaper than copper. After understanding the most important properties and factors for selecting the conductor material, we will now begin to learn about the main types of conductors or wires used in overhead transmission lines. We will start with the traditional types of conductors. The first type of traditional conductor used in overhead transmission lines is the all-aluminum conductor, AAC. The most important advantage of this type of conductor is that it is considered the cheapest among all conductor types. However, the main disadvantage of this type is its low mechanical strength. Due to this low mechanical strength, this type of conductor is suitable only when the distance between transmission towers is short, because large distances mean a greater tensile force and weight stress acting downward on the conductor. Therefore, such applications require high mechanical strength, as we explained earlier. The second type of traditional conductor used in overhead transmission lines is the aluminum conductor steel reinforced, ACSR. This type of conductor consists of a core made of one or more layers of galvanized steel wires surrounded by one or more layers of aluminum wires, as shown in the diagram in front of us. From this, we understand that this type of conductor contains two different metals, steel and aluminum. Therefore, the cross-sectional area of this type of conductor is represented by two numbers. One number refers to the cross-sectional area of the steel wires, and the other refers to the cross-sectional area of the aluminum wires. For example, 120 over 20 square millimeters, 240 over 40 square millimeters, 380 over 50 square millimeters. From this, we understand that the steel wires provide the required tensile strength and mechanical durability, while the aluminum wires provide high electrical conductivity. The most important advantage of this type of conductor is that its mechanical strength is much higher than that of the previous type, AAC. Therefore, it is used when the distance between towers is large. As mentioned earlier, when the mechanical strength of the conductor is high, it can withstand greater mechanical tension caused by its own weight, especially over long spans between towers. An important point to note is that this type of conductor can withstand temperatures up to 80 degrees Celsius, and if the conductor's temperature exceeds this limit, its mechanical properties will begin to change and deteriorate. The third type of traditional conductor used in overhead transmission lines is the all-aluminum alloy conductor, AAAC. This type of conductor is made from an alloy of aluminum, magnesium, and silicon. The first important advantage of this type which makes it superior to the previous two types, AAC and ACSR, is that it has very high mechanical strength. This means that the conductor can withstand very high tensile forces, allowing for larger spacing between towers. Consequently, fewer towers are needed, leading to a reduction in overall construction cost of the overhead line. The second advantage of this type of conductor is that its electrical resistance is lower than that of the ACSR type. Since lower resistance means lower power loss and less voltage drop, this leads to better line performance and improved efficiency. Therefore, we find that most modern overhead transmission lines currently use this type of conductor, AAAC. It is also important to know that this type of conductor can withstand temperatures up to 90 degrees Celsius. The fourth type of traditional conductor used in overhead transmission lines is the aluminum conductor alloy reinforced, ACAR. This type of conductor is very similar to the ACSR type, with one key difference. In the ACAR conductor, the steel core wires used in ACSR are replaced with wires made of aluminum alloy. This modification gives ACAR conductors better overall properties compared to ACSR conductors, both in terms of mechanical strength and conductivity. The fifth type of traditional conductor used in overhead transmission lines is the aluminum alloy conductor steel reinforced, AACSR. This type of conductor is also very similar to ACSR conductors since both types contain a steel core. However, the difference between AACSR and ACSR conductors is that the outer aluminum wires in ACSR are replaced by aluminum alloy wires in the AACSR type. As mentioned earlier, the aluminum alloy is composed of aluminum, magnesium, and silicon. Therefore, AACSR conductors have very high mechanical strength, but this comes at the expense of conductivity, meaning that their electrical conductivity is lower. Because of this, many electrical engineers prefer to use this type of conductor as earth wires or ground wires in overhead transmission lines. Next, we will explain the different types of heat-resistant used in overhead transmission lines conductors. As everyone knows, there is a continuous increase in electrical power consumption, and the common or logical solution to meet this growing demand for electric energy is to construct new transmission lines. However, there are two main problems with this approach. The first problem is the high economic cost of constructing new transmission lines. The second problem is the difficulty of finding new right-of-way routes or suitable paths for these new overhead lines. Therefore, engineers started to think about increasing the power transfer capacity and enhancing the transmission line capability by replacing the existing conductors with conductors having larger cross-sectional areas. But here comes another issue. Replacing the existing conductors with conductors of larger cross-sectional areas would increase the mechanical tension on the towers due to the added weight. Hence, the best and most practical solution was to use new types of conductors that have the same cross-sectional area as the existing conductors being replaced, but which can carry higher electrical current and transmit more power. This means that these new conductors must be capable of withstanding higher temperatures resulting from the increased current or transmitted power, without requiring any reinforcement of the existing towers. However, it is extremely important to maintain the same level of sag in the new conductors. For this reason, new conductors known as heat-resistant conductors were developed. In general, these are conductors that can withstand high temperatures, typically above 150 degrees Celsius, and in many cases up to 210 degrees Celsius, 250 degrees Celsius, or even higher. By using these heat-resistant conductors, it is possible to increase the power transfer capacity or line loading capability by more than 50%. However, a very important question arises. Does the use of heat-resistant conductors, which may reach temperatures of 150 degrees Celsius or even more than 210 degrees Celsius, affect the insulators, clamps, and other accessories of the overhead line? Of course, the answer is yes. All components and accessories of the overhead line will be affected when heat-resistant conductors are used, and the most affected element is the line insulator itself. Therefore, this factor must be taken into careful consideration. Based on numerous experiments and research studies, the following observations have been made. When the conductor temperature reaches 180 degrees Celsius, the temperature of the porcelain insulator and its fittings increases by approximately 10 degrees Celsius to 20 degrees Celsius above the ambient temperature. When the conductor temperature reaches 200 degrees Celsius or higher, the temperature of the porcelain insulator and its fittings increases by approximately 30 degrees Celsius above the ambient temperature. Hence, it is essential to carefully check the maximum allowable temperature limit for both the insulators and the overhead line fittings. Now, let us learn about the most important types of heat-resistant overhead line conductors. The first type of heat-resistant conductor is the temperature-resistant aluminum conductor steel reinforced, TACSR. This type of conductor consists of heat-resistant aluminum conductors reinforced with steel. These conductors are very similar to ACSR conductors, but the aluminum used here is an aluminum zirconium alloy. The presence of zirconium allows the aluminum to retain its mechanical properties even when exposed to high temperatures. It is also important to know that this type of conductor can withstand temperatures up to approximately 250 degrees Celsius or even 300 degrees Celsius without losing its mechanical properties. Another important point is that the maximum temperature this conductor can withstand depends on the amount of zirconium in the alloy. This means that as the percentage of zirconium increases, the maximum allowable temperature also increases. However, we must note that the presence of zirconium slightly reduces the electrical conductivity of aluminum by approximately 1%. The second type of heat-resistant conductor is the aluminum conductor steel-supported, ACSS. This type of conductor consists of a core made of steel wires surrounded by one or more layers of aluminum wires. This means that ACSS conductors are similar to ACSR conductors, but the aluminum used here undergoes special annealing processes in the factory, making it soft and fully annealed. This type of conductor can continuously withstand temperatures up to 210 degrees Celsius. Among the most important advantages of this conductor are high mechanical strength due to the steel wire core, low coefficient of thermal expansion, which means that the conductor does not expand significantly in summer or at high temperatures, nor shrink excessively in winter or at low temperatures. The third type of heat-resistant conductor is the low-sag composite core conductor, LSCC. This type of conductor is characterized by having a carbon fiber core, which contributes to reducing power losses. The main advantages of this type of conductor are low coefficient of thermal expansion, which results in less sag, suitable for long spans, meaning it is used when the distance between towers is large, can withstand temperatures up to 180 degrees Celsius. The fourth type of heat-resistant conductor is the aluminum conductor composite reinforced ACCR. This type of conductor has a core made of resin-based materials such as fiber composites, which possess very high mechanical strength compared to iron or steel. It is also characterized by having a low coefficient of thermal expansion, meaning that it does not expand during summer or high temperature conditions and does not contract during winter or low temperature conditions. Another important advantage of this type is its high resistance to corrosion. These conductors can continuously withstand temperatures up to 210 degrees Celsius. The fifth type of heat-resistant conductor is the aluminum conductor composite core, ACCC. This type of conductor is similar to ACSS conductors because it also consists of annealed aluminum wires that can withstand temperatures up to 220 degrees Celsius. The core of these conductors is made of a resin-based composite material that provides high mechanical strength. One of the most important features of this conductor is its low coefficient of thermal expansion, which means that it does not expand at high temperatures, resulting in less sag even when temperatures rise. As mentioned earlier, this type of conductor can withstand temperatures up to 220 degrees Celsius. The sixth type of heat-resistant conductor is the gapped super thermal resistant aluminum alloy conductor, galvanized steel reinforced, GSTACSR. This type of conductor consists of a core made of galvanized steel wires that have high mechanical strength surrounded by one or more layers of aluminum alloy wires that are trapezoidal in shape. As we can see in the illustration, there is a gap or space between the steel core and the inner layer of the aluminum alloy. This gap is filled with grease, which serves an important cooling function by helping to dissipate heat when the conductor operates at high temperatures. Finally, this type of conductor can withstand temperatures up to 210 degrees Celsius. The seventh type of heat-resistant conductor is the super-thermal resistant aluminum alloy conductor INVAR reinforced, STACIR. This type of conductor contains a core made of wires composed of an iron-nickel alloy. The most important property of this alloy is that it does not expand with temperature, and that is why it is called INVAR, which stands for invariable to change of temperature. In addition, this conductor has one or more layers of aluminum alloy wires, where the alloy is composed of aluminum, magnesium, and silicon. This alloy is capable of withstanding high temperatures up to 220 degrees Celsius. Among the most important advantages of this type of conductor are its low coefficient of thermal expansion, which results in less sag at high temperatures. Now let's talk about the most important data or technical specifications of overhead electric power transmission line conductors. First, we have the conductor material, which can be copper, aluminum, or steel. Next, we have the number of wires that make up the conductor. It could be aluminum only, or a combination of aluminum and steel, which we refer to as aluminum over steel. Then, we have the cross-sectional area, often written as CSA. For example, 400 square millimeters, or sometimes 380 over 50 square millimeters when we have a composite conductor. After that, we specify the overall diameter of the conductor, measured in millimeters. Another important parameter is the resistance at 20 degrees Celsius, and that's expressed in ohms per kilometer. We also look at the rated current, which is given in amperes. Then comes the maximum short circuit current, written as SC and measured in kiloamperes per second. We also record the conductor weight, measured in kilograms per kilometer. Next, we consider the maximum tension on the conductor, measured in kilonewtons. And finally, we have the conductivity and the heat expansion coefficient, which describe how well the material conducts electricity and how much it expands with temperature changes. Thank you for your attention. See you in the next lecture.